Let's try a few more examples for calculating antiderivatives. And this time we're going to use, or at least keep in mind, these elementary form that we just discussed. All right, so let's start with this function 2 times sine x plus 3 times secant squared x. And we're going to integrate this function with respect to x. So we're going to calculate this integral. And so when we look at this, we should kind of start with focus in on the addition and subtraction signs. That kind of splits up our function into distinct terms. And so when we look at this, I kind of see two terms here. I see this 2 times sine x, and then I see this 3 times secant squared x. And so what we're going to do is we're going to focus in on differentiating each of these terms individually. So let's start with this 2 times sine x. The 2 is a constant multiple, so we can kind of focus in even further on just this sine x term. Let's get the antiderivative of that. And so if we go to our table, what is the antiderivative of sine x? Well, it's negative cosine x. So for that first piece, we're done integrating. So it'll be 2, and then the antiderivative of sine, if we look at our table here, negative cosine. Okay, we'll save the plus c until the very end. All right, so that's this first piece, this first term. Then we have plus, and then 3 is another constant multiple. And we get to our second term, and now we focus in on just the variable part there, so secant squared x. We look, I see secant squared x right here, and its antiderivative is tan x. And that takes us to the end. We're done integrating. That's our last term. So now we put plus c at the end. Perfectly fine for our antiderivative. I would probably clean this up a little bit. So this negative cosine, I would actually put the negative in front with the 2. It's easy that when we have these negative multiples like this, this can easily become subtraction, and it's not. So I would rewrite this as negative 2 cosine x plus 3 times tan x plus c. And there's our antiderivative. All right, let's try another one. Here we're using theta as our variable, so not x. And we start by just kind of identifying our terms. So there's a plus sign here, which is really telling me, all right, there's this piece of my function. This is my first term. And then this is my second term over here. And so we can handle each of these completely separate. So this might take one strategy. Doing this piece might take a completely different strategy. All right, so first of all, we have cosine over sine squared. If I go to my elementary forms here, I don't see that anywhere. So we might try to get started with this one. We might try to break this function apart and use some trig identities to try to get it into one of these forms. So let's try and do that. I might split this up into cosine theta over sine theta times 1 over sine theta. And, you know, this is definitely equivalent. So sine theta times sine theta is sine squared. When we multiply fractions, we just multiply the numerators, multiply the denominators. All right, well, that maybe isn't getting us anywhere quite just yet. But then cosine over sine, that's actually cotangent. So that first fraction is cotangent theta. And then 1 over sine, that's cosecant theta. So we're just using some trig identities here. That's always a strategy we can use. And now, this first piece, we've turned it from cosine theta over sine squared theta into cotan times cosecant. And if we go to our list of elementary forms, I see that right here, cotan times cosecant. So we're going to be able to integrate this. All right, so what about this second piece? What might we do over there? Oops. Well, this 5 is just a constant multiple. So usually it's helpful to try to separate that off. So I'm going to pull that 5 off and write this as 5 times 1 over 1 plus theta squared. So I did some work over here with some trig identities. Now what can we do over here? Well, this 5 times 1 over 1 plus theta squared, this 5 is a constant multiple. And so I'm just looking now for this kind of variable piece. And I see that right over here, 1 over 1 plus x squared. That's going to be inverse tan. So we're at a point now where we're ready to go through and integrate each of these. So what is the integral of cotan theta times cosecant theta? Well, that's right here. Integral of cosecant x times cotan x is negative cosecant. So this first piece is going to be negative cosecant theta. Remember, we're using thetas. Then we have our 5, which is a constant multiple. And then what's the antiderivative of this 1 over 1 plus theta squared? Well, that's right here. Integral of 1 over 1 plus x squared is inverse tan. So this is going to be 5 times inverse tan of theta. And then we put our plus c. We save that for the very end. And there's our antiderivative. So a couple strategies here. If we have a fraction, it's helpful to try to break the fraction apart. And especially if we have some trig functions, try to use trig identities if you have something that's not immediately recognizable. Also, when we have fractions, it's helpful to pull off the constant and kind of separate off the variable part so that you might get something more recognizable. And then we get to a point where we're ready to integrate. And so notice then, because theta is our variable here, our answer has theta as well. All right, let's try another one. Let's do the integral of 5 times e to the x plus x times square root x. And so when we look at this, again, the addition and subtraction signs are really splitting up the different pieces of our function in terms of how we integrate. So when I look at this, my first term here is 5e to the x, and then my second term here is x times square root x. So 5 times e to the x. 5 is a constant multiple, and I can just look up what the antiderivative of e to the x is. So this first term is not going to be a problem. The question is, how do we handle this second piece where it's a variable times a variable? And this is not constant multiplication here. There is some multiplication going on in between these two x terms, but it's multiplication. It's x times square root x. And so if we were going to differentiate this, how would we differentiate it? Well, we would try to actually combine these into one single power function. And so the same idea works here. Instead of trying to integrate these separately, we can actually combine them into one single power function. So this x times square root x, we can write this as x times x raised to the 1/2 power, which is then x raised to the 3/2 power if we add the exponents. So it's a similar strategy as to what we would do if we were trying to differentiate this thing. All right, so rewriting our function, we can write this as 5 times e to the x plus x raised to the 3/2 power. And now we're ready to integrate. So we have this first piece here, we have our second piece, and what is the antiderivative of e to the x? We see that right here, it's just e to the x. So the antiderivative for this first piece is 5 times e to the x. 5 is a constant multiple, so it just kind of sticks around. We focus in on this e to the x, get its antiderivative, just e to the x. Then we go on to our second term. We have x raised to the 3/2 power. That's just power rule. So we add 1, or we keep our variable the same, x, add 1 to the exponent, so that's going to bump us up to 5/2. Take this new exponent, flip it, put it in front, so 2 over 5. So we have the antiderivative of our first term plus the antiderivative of our second term, and it's plus because that's what our original function had. And then we put a lone plus c at the end there. All right. Going on to the last one, when we look at this, what I'm seeing is, again, two separate terms. I have this fraction here, t squared plus 1 over t, then plus, and then I have a second term here, 7 times cosine t. So this second term is not too bad. It's a constant multiple, and then we just focus and integrate cosine. We can just look that up or have it memorized. The first term here might cause an issue, and that's because we have a fraction. And in this fraction, there is t terms, there's variable terms on the top, and there's variable terms on the bottom. So we haven't seen, just as up here, we haven't seen how to integrate when we have multiplication of two variables. We have to do something first to simplify this. Same thing down here for division. We don't know yet how to handle integration when we're dividing variable terms. So we want to try to simplify this kind of similar along the lines of what we did up here. And so we have division. And so what we're going to do is we're going to take that fraction where we have the division, and we're going to break it up into two separate fractions in this case. So it'll be t squared over t plus 1 over t. And then if we simplify those, the first one here is 1. And then 1 over t we're just going to leave as just 1 over t. We maybe get that as, or sorry, this is going to be t rather, not 1. So we get t squared over t is t. And 1 over t, we're actually going to leave that one as is. And the reason is because 1 over t is kind of something special. I mean, we could rewrite this as t raised to the negative 1. I think it's a little bit easier to leave it as 1 over t, just because it stands out that that's something more recognizable. So when we go to integrate this, this fraction t squared plus 1 over t actually becomes t plus 1 over t. And then we have plus 7 times cosine t. And we're integrating this. And so now when I look at this, now we actually have three distinct terms. So we're just going to go term by term and integrate each of these. So the first one, power rule. What is the antiderivative of t? Well, we write down our variable, add 1 to the exponent, so that bumps us up to 2. Remember, there's kind of a hidden exponent of 1 here. Take this new exponent, flip it, put it in front, so 1/2 t squared. That means we're done. Now we go on to the next one. There's a plus sign in the middle, so our antiderivative has a plus sign. What's the antiderivative of 1 over t? Well, we can look that one up, and we see that right here. 1 over x is natural log absolute value x. So we're going to have natural log absolute value t. Done with that second term. Now our function has a plus, so we have another plus. 7 is a constant multiple, so we can just focus in on that cosine t term, our variable term. What's the antiderivative of cosine x? It's sine x. So we're going to have plus 7 times sine of t. And then that's the integral of our last term. So then plus c at the very end. And so again, we've just gone term by term to integrate these, and then we're remembering our plus c at the very end. And the only thing kind of tricky here is, since our function had this division term, this fraction where there was variables on the top and bottom, we kind of had to do something with that first. And also because it's not one of these two, we had to do something to get it into a form that we could actually integrate. So something similar to what we did up here with this multiplication. All right, so we're going to stop there. In the next lesson that we're going to see, we're going to practice more integration, but we're going to investigate this idea of this arbitrary constant plus c. So we're going to see in what context are we actually interested in figuring out, okay, what is this constant c at the end exactly? So we're going to see that next.